Okay, what we're going to do now is we're going to show a video, 2 minutes. I'm going to kind of talk us through it. And we're going to use that problem to run a common thread through the rest of the day, rest of the morning here. Now here we see a head-up display. And to help orient us, we've got some stop action there. This is the actual event that's occurring here on the screen on the left. That's the horizon line that we see there. The airplane is in a slight left turn. He's got a slight nose, high attitude. He identifies the target and he goes into a high energy maneuver. And he's actually in a 90-degree angle to bank, pulling 7 Gs. Now watch the G meter, which is on the left-hand side. Now he's pulled 7.2 Gs at this point. At this point, G-lock occurs, which is G-loss of consciousness. Now watch the nose fall through. The nose is going to fall through. He's going to go into what we call a dead man spiral at this point here in the mission. Cruise situation is totally lost. He's lost sight of the bogey, and we have, in fact, mission failure at this point. Now, at this point, the instructor pilot in the back seat begins to recognize that something is seriously wrong. He's approaching the terrain. This is over the southwest, so it's a fairly high terrain. He's approaching the terrain at a very high speed. Now watch the speed build up on the right-hand side. The right ladder, I'm sorry, the speed is on the left-hand side. Now at that point he's going 600 knots, nose low, heading right for the rocks. Now recovery starts here, and the recovery is kind of dramatic. Airspeed, altitude get down to 8.5 or 8,500 feet, which is, considering the terrain at about 5,000 feet, is fairly close. And that's the end of the video. What we saw was a high-energy maneuver that produced G-loss of consciousness. Let's use that to create a scenario here. Let's assume that we are now part of this design team that's been brought in by the Air Force to assess this problem. Okay, the Air Force says, okay, industry, we have a problem here. We don't know what to do. So we've been brought in. We're a hybrid team. We don't have any prejudices. We are not tied to any particular technology. We've been brought in to define the problem first, to the best of our ability, and then come up with a conceptual solution. And that's what we're going to try to do today, is to define the problem to the best of our ability, and then to come up with a conceptual solution, and then hand that off to designers and engineers to see if we can come up with a good, solid design. What we have, essentially, now, we have 2 major functions that we are involved with in this event: energy management and flight trajectory. And what we have done in this design now, we've coupled those functions together through the head-up display, right? So the coupling recipe in this case is the head-up display. We saw the G meter on the left, and we saw the airspeed ladder and the altitude ladder. So we're coupling flight trajectory with energy management through the HUD. We don't know if that's a good idea or not, but let's take a look at it. That one right there. As a Tiger team, what do we need to know about this situation? Okay, our first meeting, let's assume this is our first meeting now. And we have got to figure out, okay guys, what do we need to know? Remember, we're not going to immediately go to a solution. We're going to stay at the operational level as long as possible. We're going to try to figure out what we need to know. And together we decide, let's assume for the moment we decide that we need to know at least these kinds of things. All right, we need to know what are the tasks, the task loading, information requirements that the crew needs to perform this particular part of the mission. And this is particularly important because we are in the heart of the air combat mission at this point. Okay, this is likely the highest task loading area of the mission. certainly one of the most critical areas of the mission. So let's say that we decide that we need to know that. We need to know these kinds of things, and then our next order of business now is to figure out how to get this information. Okay. And this goes into our first module. Our first module today is called Mission Decomposition. What we're trying to do here is we're trying to identify the operational data. We're trying to understand the mission. We want to characterize the mission to figure out what is going on in the air combat mission, what are the tasks and activities, objectives that the crew is faced with. All right? We step back just for a minute and remind you that the crew identified a target at 11 o'clock, went into a high energy maneuver, and at that point we had mission failure. Why maneuver? Why did we do that? Okay, we need to understand what the mission is demanding. Now here, what I'm trying to explain here is that while we are doing this, while we are trying to decompose the mission, to understand the mission, we've got to keep one thing in mind, is that we have an integrated system that we're dealing with. We have integrated, for example, energy management with maneuver trajectory control, or energy management with maneuvers. We have actually integrated that. We've integrated that through the HUD with the man in the loop in this particular airplane situation. All right? And we have an integration problem, fundamentally an integration problem, but we don't know exactly what it is yet. So the next order of business then is, okay, we have one of our team members or groups go out and decompose the mission. Try to figure out what specifically are the mission objectives and what are the tasks. What exactly are we dealing with here from an air combat situation? So there are techniques that we can use, tools. Here is a template that we can use that explains how one might go about decomposing the mission. Here we have the air superiority mission. In this case, we're dealing with air combat maneuvering. And certainly there are the tactical activities, and they are target area activities. Remember, we have completed the ingress to the target. We have acquired the target, and now we are engaged with the target at this point. Okay? And we are maneuvering. So we are in the maneuvering part of the mission. So one of the mission objectives certainly is maneuver against target. We agree with that, right? That's pretty self-evident. We're maneuvering for the intercept. And actually what we're doing at this point is what we are trying to understand the intercept geometry, and we're trying to achieve an advantageous position. And we're going to be focusing on this guy right here for the rest of the day. Analyze intercept geometry. Why did we go into a hard left turn? Got to be some reason, right? So we're going to analyze the intercept geometry and see if we can begin to deal with that. And let's again assume for the moment that we decided we're going to focus on that particular task of the mission. The mission decomposition is right there. Let's put that one up. The mission decomposition. For reference, we have decomposed the whole air combat mission here. And this is for reference, and we did that because we wanted to prove, let's say, to the customer that we knew exactly what was going on in the whole mission, all of the tactical areas. But we're going to focus on one mission objective today. We're going to focus on maneuver to intercept target 6.0 because we're in the maneuvering portion of the mission. And we're going to be focusing on those particular tasks associated with the maneuver portion, or 6.0. Specifically, we're going to be looking at, here's maneuver to intercept again over here, and we've decomposed that into its constituent parts. Specifically, we're going to be focusing on, for the rest of the day, 6.1.1, which is analyze intercept geometry. We feel that that's pretty important because it's complex, difficult to do, and it really sets the stage for success or failure. If we analyze the intercept geometry incorrectly, and we're kind of leading up to that this is the case in this problem event. If we analyze that incorrectly, we're probably not going to succeed in combat. How do we know that we've got our bases covered? How do we know that that is in fact what the tasks are for that particular part of the mission? And we wanted to make sure now as a design team that we could confidently go to the customer and say, yeah, this is what we're dealing with here. This is the essential part of the mission. In this case, what we've done here is we've done a little validation check on our thinking. We've gone to the fighter weapons school at Nellis or at Miramar Top Gun, and we said, okay guys, what do you teach? What do you need to know? What does a fighter pilot need to know about this situation? The first thing that he learns is what the particular campaign goals are. What is the situation that he's dealing with? And then what are the general tactical objectives? Those are listed on the top. We take those and we place those in process terms. The crew in this case has to understand the situation. Now you notice down here at the bottom we have our mission objective 6.0, maneuver to intercept targets. What is the crew doing here? What is the man, the intelligence system now in our case, doing? Well, he's doing essentially three things, or performing three processes that he's taught to do in Top Gun. He's taught to understand the situation, situation awareness, and they'd have elaborate training programs to teach that. So he learns to do that process. He is also learning plan formulation. He's formulating his attack plan. Even before he acquires the target, he's got a plan that's being worked. He probably had a plan before he launched, right? Probably had an idea what his threat was going to be. So he had a plan. So he's processing a plan. And then, of course, in his maneuver, he's executing that plan. What we want to focus on today is situation understanding, or situation awareness, because that relates to this guy right here, which is analyze intercept geometry. We're going to analyze the intercept geometry within the context of trying to understand the situation. One more check. We wanted to make sure that we had enough graphics to cover our Air Force brief. And that's kind of a neat little graphic there. But it's a nice double check on our thinking, too. What we've done here is we have kind of organized our thinking in a little bit different way. We have the tasks listed along the top, as you see. And we've organized it in the context of, okay, there are certain problems that we have to solve, and there's certain solutions to the problem. There are sub-problems and there's sub-solutions, and finally we come up, hopefully, at the end here with some kind of a terminal solution that represents the problem, or that we claim solves the problem. That's all we're trying to do here, is just kind of double-check our thinking, making sure that we've got all the bases covered when we present our findings to the customer. All right? And our findings are that we have this task data now. And it's raw data because we're going to do a lot with this task data. But we have this task data. We're fairly confident that this task data represents in static form what was going on here in dynamic form. And we're going to try to give this task data, which is static, some life to it for the rest of the day. And we're going to try to use that to help us understand how to build up the conceptual design to come up with a solution. Now that's it for the mission decomposition module. What I want to do here is, after each module, I want to take a very short break and see if there's any questions or any comments that you might have. I like to get, you know, some good interaction going on this thing. We're going to be here for a while, so we might as well enjoy ourselves. So let's do that. Obviously, we're going to be somewhat constrained because they are videotaping us, but let's try to get some, you know, thoughts out. Any comments at this point before we go into the next module, which is the critical task analysis? That module, by the way, is going to try to give some life to the static decomposition data. Go ahead. Yes, sir.
You had a list of functions that the pilot will perform in air-to-air combat in the left forward, and the last item was identify the target. It seemed to be out of order after target acquisition.
Was that the earlier, one of the earlier charts?
Yes.
It may have been. All I was trying to point out there was that you were dealing with an integrated system, okay? That these should not be viewed in isolation, but one integrates with the other. And I was trying to point out that the energy management really is a task that continues through the whole maneuvering part of the mission, okay? And there are other things that impact on that. You have to do other things. You have to manage your flight path as well as manage your energy, and it becomes very complex. That's the only point I was trying to make. They may have, one of those may have been out of sequence, but the point I was trying to make was we are dealing with an integrated system here, and we've got to approach it not from the discrete component approach, but from the integrated approach that Graham was trying to explain earlier, okay? The next order of business then is critical task analysis or criticality analysis. What we need to have an idea of, we think, is now that we have these static tasks, what do you do with that? And how do these tasks relate to the success of the mission? How do they relate to such factors as task loading? What is the task loading? If you come to me and say, geez, Kevin, boy, the task load is pretty high here. I can appreciate that, and that's intuitively obvious to me because I used to teach this subject, but I can't do anything with that. Okay, high is not a good data point. So we need to get thinking about how we can quantify, analyze the mission from a quantified standpoint, try to put some values or numbers, or try to come up with a task loading value, for example, or a task interaction value that means something to us that we can use. And we can use that kind of as a discriminator too, to look at the whole mission and find out where the critical areas are in the mission. How does one do a critical task analysis, or how does one do a criticality analysis? It's our feeling that a criticality analysis is a multidimensional construct. It involves many things. But I think we can define them. And this is a definition that we have constructed to help us come to grips with this pretty important area, critical task analysis or criticality analysis. Basically what we have is this. We have a situation where task may be difficult because of things going on. For example, there's not a lot of time to do the task. In that video we saw that there was pretty high time compression, and other things are going on. That all relates to this notion of task difficulty. We combine the notion of task difficulty with the notion of mission phase importance. The reason why we do that is because there may be some tasks that are in fact difficult, but they may not be in as an important area of the mission as other tasks. For example, in-flight refueling. In-flight refueling might be a difficult task, but it is not in a portion of the mission that is as important to mission success as, for example, this portion here that we saw in the video, which was target intercept. So that helps us discriminate between the difficult tasks and the truly critical tasks. So it gives us a number of ways to look at it. We combine those values, and we're going to give those values today. We combine those values and come up with our notion of mission criticality. And we're going to use that, hopefully, to help us in our design. We're going to use that to help us understand where to focus our design efforts. Okay, and we're going to come up with some numbers to help us. Let's leave that up there. Let me switch over to this chart for a second. First, we're going to look at the notion of task difficulty, and we think task difficulty is a three-dimensional construct, as we show here. We think task difficulty has a lot to do with time compression, or the time available to perform the mission or the task. We think it has a lot to do with interaction. Are there interacting tasks? Do you have to do two or more tasks together, for example? And then, last but not least, and maybe in fact most importantly, cognitive or processing complexity. How complex is this task to process? And we know from decision theory that some tasks are more complex to process than others. Okay, we're going to combine those using multi-attribute utility theory to come up with a number or a value or a rating, if you will, to see if we can use this to help our design. The first order of business is looking at time compression. Now, there are some tasks that have to be done very quickly, obviously. And in this case, I think, in this video case, I think we're seeing a number of tasks that have to be done very rapidly. So we have what we call a compressed time condition. Conversely, we may have other tasks, like when he was ingressing to the target, rendezvousing with his wingman. You could consider those tasks to be less compressed or in a relaxed time condition. So we have those two notions here that we're going to be playing with when we try to understand task loading. How do you analyze time compression? Simple timeline analysis would perhaps be sufficient here. Bring in a subject matter expert. Let's assume that part of the team is, in fact, subject matter experts. We have an instructor pilot from Top Gun as part of our Tiger team, and he helps us construct a timeline. The timeline can be as general as this. This is a very general timeline here that we see. The time slice that we're dealing with is 460 seconds that you see on the left. It could be a very specific timeline, like you see over here on the right. This is a complete intercept, very complex. I don't want you to read the whole thing. I just throw that up there to let you see that it can be as detailed as that. Okay? You can get right down to the, almost to the nanosecond if you wanted to. We don't really need to do that, but certainly the 0.5 seconds, okay? Because we think dwell time has to do with about 0.5 or 0.6 seconds. So we can get that detailed. And we can organize our thinking into time slots. And this is the way we've done it here in this example. This actually is a high-altitude intercept. The fighter is coming off the cap that you see on the left. He's intercepting a supersonic bomber on the right. And we've organized our thinking into time slots so that between C and D, and this is what we're going to be dealing with today, between C and D we have a time slot that we're dealing with, all right? And the time slot is 83.3 seconds, right? Everybody see that? And we can organize our thinking here. We can put this rather complex graphic in tabular form. This is just a tabular representation of what you see here for our report. All right? And we identify the time slot, and here you can see at event D, we do have that time slot of 83.3 seconds represented. We also have the time slots for the whole mission because we wanted to show the customer that we understood the whole air combat mission too, okay? So we didn't leave anything out. So that's how we look at the time compression. Now, we can analyze that using, and we have various rules and ideas, rules of thumb, of how to determine if you are in a compressed time or a relaxed time condition. Essentially what we have, remember we had the two time conditions. We had the relaxed time over here and the compressed time over here. What we need to understand then is where does that crossover occur between relaxed time to compressed time conditions? And certainly that's situation dependent, right? For example, if you were on a deck launch intercept, you may be immediately catapulted into a compressed time condition and you would stay there for the whole mission, correct? In our case here, we see that we leisurely go into the cap station and leisurely go into a holding pattern, and the compressed time condition would occur after we received the order to intercept the target and things started to happen in a rapid fashion. Okay. From an analytical standpoint then, we want to look at at what point in the mission then do we have this crossover, because that's going to help us give this a value or a weight in a minute. In this case, I think we can fairly well determine that we have a crossover somewhere there in the maneuver to intercept phase of the mission. All right? Now, we really don't know what happened, but let's assume for the moment that the airplane did in fact come off a cap station. He was already at 22,500 feet, and then he got the intercept from the AWACS airplane. Okay, the target 11 o'clock, and then he performs a maneuver for intercept. So let's say at that point we had crossover between a relaxed time condition and a compressed time condition. See, I need to scale that. Where's my rating scale? Where's my rating scale on that, Graham? I need to scale that before. Oh, okay, I'm not going to do that yet. Okay, yeah. I got way ahead of myself for a second. All right, next one then.